Alrighty, welcome everyone to our CRISiSLab webinar. And can't believe this year has already passed over half, and this is actually our first time this year. A lot of people probably know that it is due to some sudden unexpected changes of our Joint Center of Disaster Research, but here we are and ready to present something fantastic that has been going on. And as you might know or might not know, CRISiSLab is part of the Joint Center of Disaster Research at Massey University in New Zealand. I believe that people who join us, probably some of you are not in New Zealand, so maybe good morning or even good evening. And so this session, we invited our interns, 9 interns from everywhere, and they have been working closely with our CRISiSLab, our PhD students and lead of the CRISiSLab, and on some cutting-edge technological solutions to tackle on the hazards that's happening in New Zealand. For example, earthquakes, flooding, landslides, and as well as communication network issues. So you can see on the screen, those are all the technology buzzwords that we probably heard or haven't heard before. So today, hopefully all of our interns can give us a fascinating explanation of what they're doing. And at the end of this 2-hour session, we get a better idea what's available, what kind of technologies are available, and what kind of technologies we can use to tackle on the hazards. That's probably enough for my introduction. And so I will give the floor to Associate Professor Raj Prasanna to give us an overview of the program.
Okay, thanks, Alicia. Here, everyone. So it's great to have a great audience today. And I thought it is good to give you a bit of a context about what we are trying to do here, especially giving a bit of introduction to the internship program. So CRISiSLab internship program started like 4 years ago with our, most of you probably may know that we have been running college level competition, CRISiSLab challenge for the last 4 years. So we started the internship program along with that 4 years ago, where we gave internship opportunity, 1-month internship opportunity for the winners of the competition. But then we expanded that immediately. Along with them, we have given opportunity for anyone who's keen to work with us, our PhD students and researchers in technology-related themes. So we have been running this for the last 4 years. And although we haven't kind of presented to a wider audience, we have been presenting their work for internal staff and students. So this is the first time we are going kind of for a wider audience. So we thought that it is a great opportunity for them to highlight or showcase their capability and also give them an opportunity to present, because some of them are very early into their presentations and stuff like that, because some of them are still in the high school. So it's a great learning curve for some of them, and then also to showcase their work. And just to give you kind of understanding what the intern profiles looks like. So we have from high school students, some of them are winners of the last year CRISiSLab challenge. And then we have undergraduate students, and we have postgraduate students. So, and also there are some professionals as well. So we have given opportunity for all these kind of different profiles to come and do internship with us if they have some interest in the themes we have been using at CRISiSLab as research themes. Overview of the presentation. So I think, so they have been working with 4 mentors, I think, along the topics of, one is alternative telecommunication methods, alternatives to internet. And then they have been looking into landslides related work. And also they have been looking into coastal erosion related work, and also earthquake related work, and flood management or flood forecasting. So, so there are students or interns who have been looking into. You see there are a couple of students talking into these thematic topic areas, but their work has been like 2 to 3 months, and some of them have been working for 6, 7 months, and some of them will continue to work on these topics. So they are at different stages, and they may or may not be able to answer all the questions, but mentors are here, as Alicia mentioned. Later on, we can have a good discussion. So I think that's enough from me, Alicia. So over to you.
Sorry, yeah. Yeah, thanks, Raj. Now, without further ado, let's begin. So the first one will be Nethma. Nethma, please share your slides.
Can you see my screen?
Almost. Yeah.
Okay, thanks. So, hi everyone. I'm Netha Pathirana, a research intern at CRISiSLab. Today, I'll be presenting the progress of a research project led by Malinta Ranasinghe under the supervision of Associate Professor Raj Prasanna. This project focuses on using AI and remote sensing to detect flood impacts in New Zealand, especially during extreme events like Cyclone Gabriel. The goal is to develop a system that can automatically identify areas that have been affected by flood or using images and text. Floods are becoming more frequent and severe in New Zealand. After a flood, it is very important to quickly understand which areas are damaged so that response teams can act faster. But right now, this is done manually by checking satellite or drone images, and that takes a lot of time and effort. Also, there's no proper flood impact dataset available for New Zealand. So in this project, our main objectives are to build a dataset showing flood impacts, to train an AI model using drone images, and to also compare those results with information extracted from news articles using language models. Our main focus was on using drone images from Cyclone Gabriel, since they give clear, high-resolution views of affected areas. These images are ideal for training machine learning models. We decided to keep the classification tasks simple, just 2 categories, damaged and non-damaged. We manually labeled 100 drone images. 60 were damaged and 40 were not. Then we trained an AI model called ResNet 50 using a method called transfer learning. This means we used a pre-trained model and only retrained the final layer for our 2 classes. Along the way, we faced some challenges. First, satellite images like Sentinel-1 and Sentinel-2 had problems. Either the resolution was too low or clouds blocked the view. Also, they don't revisit the same location often enough during a flood. Labeling images manually was also time-consuming, especially when you're trying to build a large dataset. Finally, defining what exactly counts as damaged can be tricky. It may look different depending on the scene, and the model needs consistent examples to learn from. We ran 2 training experiments using the ResNet 50 model. The model trained for 10 epochs gave the best performance, 90% accuracy, and only 3 misclassified images. It handled both flooded and non-flooded classes equally well. The model trained for 20 epochs improved slightly in detecting flooded areas, but got worse at detecting non-flooded ones. Its overall accuracy dropped to 83%, and we saw signs of overfitting. So we selected the 10 epoch model as the better version for moving forward. Our next step is to train more advanced models like YOLO V8 and UNet, which are better for object detection and segmentation. These models will help us identify and highlight damaged areas more clearly. We plan to scale this to around 1,000 drone image tags. On the tech side, I'm also extending on Vajranath's work, using large language models to extract flood impacts from news articles. Then we will compare those text results with our image-based findings so we get a more complete picture of the flood's impact. Finally, the aim is to compile the findings and publish an article. To sum up, this research is about building a smart system that can detect flood impacts using both images and news reports. So far, I've trained an initial model using drone images, and now we are moving towards improving it with better models and large data sets. Thank you for giving your precious time and attention today.
Thank you, Nethma.
Thank you.
Yeah, if you can unshare your slide.
Yeah.
Yeah, thank you. Yeah, that's a shortish presentation. You only use 5 minutes, but that means we have more time for questions if there are any. Any questions for Nethma? Before any question, Nethma, maybe you can slightly introduce yourself a little bit, your background.
So I'm currently a final year undergraduate in data science at Sri Lanka Technology Campus. I'm also currently moving on to a new role as a data analyst at a company in Sri Lanka. So I completed my final year project in AI, site-based. It's an AI-assisted mathematics and toolkit. And currently I'm waiting for the results of my final year project. All the academic work has been finished.
Thank you. Thank you, Nethma.
Thanks.
Any questions? And feel free to drop in the chat box if you're shy, but feel free to raise your hand over here or just unmute yourself. Or maybe it's a little bit preview. First presentation is kind of like a warm up, but I'm sure maybe after several presentations and people will get more sense of what's happening. And I believe the next presentation by Vajranath, because Nethma, you mentioned that it's kind of like a work built on his work on large language models, right? So maybe after Vajranath, people can ask more questions. If there are no questions for Nethma at the moment, let's continue for the next one. Extracting historical flood impacts from unstructured data using large language models by Vajranath. So Vajranath, if you can share your screen. Talking about large language models, I know that a lot of people didn't show your face, but if you're using ChatGPT and yeah, maybe this one can be quite relevant as well. Yeah, Vajranath, over to you.
Can you guys hear me? Yes. Hi, I'm Vajranath. I just recently completed a master's degree in applied data science at the University of Canterbury. And this project was, which I did last summer as a part of the master's degree. So it's basically extracting historical flood impacts from unstructured data using large language models. So some of you guys might wondering that what are the unstructured data and what are the large language models are. So unstructured data means like newspaper articles, so there's no proper order present in the information, and it has several formats, and some of them are mostly in the text-based one. Large language models are, so I'm sure all of you are familiar with AI concepts and at least heard about AI and ChatGPT. So large language models, nothing but some kind of system like ChatGPT. Yeah. And why flood and why it is why we are talking about it. So floods are one of the major natural disasters identified in New Zealand. Because of that, once the flood is occurred, soon after a flood, the main three questions people ask is, when did it happen? So what are the affected areas? What kind of damages it has happened? So those are the basic three questions people will ask and people will talking about. So our objective was to build the proper flood impact data sets through the historical articles like the newspapers and some other publications. So which will help government agencies and disaster response teams to make timely decisions related to floods. So that's our main idea behind this project. Yes, so this is our, we use high-level methodology that we use. First, as you can see on the top left corner of the image, so those are the flood-related articles. Like for to access those articles, we use a digital NZ archive, which was provided by the National Library of New Zealand. And also they provide digital API for the developers to get the information as they require. So using that digital insect API, so we extracted the articles related to the flood-related articles, historical flood articles, and we further extracted using an LLM like a ChatGPT, which is refers as GPT for O model. And so we can instruct to the LLM to get the information as we wanted. Like we mainly focus on date, locations, the impact statement from those articles if they're available. So similarly, that is the main exercise we did. So to validate this information, we have known data sets like historical weather events data provided by NEVA. So we use this as to the validation data set. And once we capture through the information to the LLM, using the LLM, we got this information to a JSON response, JSON file, which is a particular file format which have the key value and the header and the value. So those information we imported into a database to further analysis. So that is what I represented here. So this is the image, like the database or the table output once we extracted the input. So you don't need to focus on every area of the slide, just focus on the red circles. So it might not be visible properly. The two circles, the leftmost one is the location string. So that is the exact JSON output that we got from the LLM. So where it has several fields like the river basin, address, street. So the location we captured through these headers. Then we again we segregated those information into separate database columns like that, as you can see on the right side. It has city, district, region, and country. Similarly, the impact statement also we captured like that, but we again further given that impact statement into the LLM to capture the impact. That means what are the damages that happen to houses and what are the life losses and what are the infrastructural damage like that. So the main key takeaways of this project was I had a proper understanding of why it is important to having a comprehensive data set when it comes to the disaster management landscapes. Also, from the technical perspective, I learned the Python-based ETL workflows and the proper usage of MDIs. And also, this is quite new thing to me to getting used in the large language model like ChatGPT in programming context and how that. So we usually use ChatGPT kind of in the web-based manner, but here it's went into the code level and how it's being used in the code, and also how to get the proper output in the prompt engineering. So that was the key takeaways I got this project. Thank you very much. Open for question.
Yeah, thank you, Vijayanath. I have a question before anyone else had. I want to ask you, yeah, maybe later, because Nathma and Vijayanath, both of your mentor is Melintha. So maybe later on Melintha can give us an overview of your project and how these two.
Oh, lovely. I have filled out a few weeks ago and I've still got this sort of, I don't know, thing. Anyway, I'll try not to too much. Hey, thinking of you, and I really everything is going really well for you and you're starting to get some of that crap sorted out, and really exciting about getting an interview for that other thing in that pinprick in the ocean, which I had to Google, and that'll be an experience. So fingers crossed. I know I'm talking now and you might think, well, shit. But anyway, I hope let me know. And I also hope that sort of those bastards out and that's sort of coming together. Really loved your face. A mixed bag, a bit of trash and treasure, but pretty amazing.
Oh. Caroline, okay. It's ironic that a technology hiccup happening in a technology presentation. That's typical. Anyway, so my question is, so how can we utilize this kind of ChatGPT? So for example, if we want to know more, if we can do a little bit exercise on our own using this unstructured wordings from maybe media. So for example, we all know that yesterday an magnitude 8.8 earthquake hit Russia pretty badly. So I believe all of our media is rushed, flooded with all those information. So on an individual basis, how can we utilize this kind of technology and maybe do our own a little module or research?
Yeah, for these particular projects, we used to analyze the historical data. So, but the question you're asking, kind of how can we use that in the real world and the real time?
Yeah,
that is one of the good areas that we might look at. But for this particular project, we only focus on the history records. But I'm not quite sure how it can be used. I mean, basically we can ask like the ChatGPT web-based solution, like that the news there may be several news regarding that the space incident. So we can have give a simple prompt to ChatGPT, like say, give me the latest development of the incident happened yesterday. So what is the recent warning issued in the New Zealand context, like that. So it will summarize and get you the required information in that case. So that is one thing that I can come to my mind. Then how should I ask?
Yeah, thank you. And now we have two questions in the chat box. The first one is from Gavin. Have you also seen and utilized Environment Canterbury's flood imagery register? And he provided a link.
I guess I can.
Oh, Melintha? Yeah, you. Yeah.
So that to have you seen this? No, this is the first time that I kind of saw it, but this is very promising, I guess. Yeah, we could use these photographs to kind of develop models or like yeah, inform our research as well. Yeah, this is very good. And then to answer Derek's questions, so for Netman and Vajranath, it's basically preliminary work. of my research to so in New Zealand, we don't have a disaster damage and loss database for natural hazards. So we are kind of planning in the dark. So there were a few articles about why we need a disaster damage and loss database. So I kind of thought how we can use like AI to kind of help us get there to create a centralized database for disaster damages and losses. So with this Vajranath's and Netman's work, I'm also like exploring other directions to how to kind of we can create a database there. So they just explore these two avenues using remote sensing data, and the other one is using text-based data to kind of create an archive of impacts for specifically for floods, but we can apply this for other natural hazards as well. So the theory behind this research was that the best practices, we haven't come up with any best practices yet, but we found that it's very hard to use satellite images because they are very low in resolution and has a very like varying revisit time, a frequency of visit over New Zealand. So just the resolution is about the maximum that you can get out of freely like open source satellite data is 50 meters, which is not granular enough for us to get a very detailed level of understanding of the flood impact, such as damages to bridge. We can't tell because a bridge is like 5 meters wide, and the pixel of a satellite image is 50 meters, so it's very hard to tell the damage from there. And so those were our learnings, and then we use this data set published by Lens of drone images to continue Netman's work, and has done some amazing work. Yeah. So
cool. Yeah. Thank you, Melintha. Yeah, thanks for the answering. And Sarah also tried to provide some of the images. So yeah, just have a look at the chat box. Okay, let's continue. Our third presentation will be done by Tasvia. The presentation title is Creating an Earthquake Catalog Using Raspberry Shake Data in New Zealand. Please share your slides, Tasvia.
Yes. Can you see the slide? Okay. I'm Tasvia Jaman Samiha. I am currently a fourth-year undergraduate in computer science and engineering, studying in Khulna University of Engineering University, Bangladesh. So I'm working in CRISiSLab for the past 6 months, and here is my project. So basically, the project is to create a database that has all the earthquake information that has occurred in New Zealand for the past 5 years. Like, let me give you a short overview of what I'm doing. Okay, so before starting, I'm giving you a simple overview of how I collected my data set. Here you can see when an earthquake happens, it releases a wave through the ground that travels to the ground, and there are different types of sensors you can see, like raspberry shake sensors and other sensors. They record the different kind of earthquake parameters, like its epicenter, the magnitude, and the latitude, longitude of that earthquake, the time, and other relevant things. So the data that is preserved in these sensors, I had to collect the earthquake waveform, like you can see it below. This earthquake waveform, I had to create a complete database of this earthquake waveform. So before starting that, my first task was to create all the stations that are located in New Zealand. And you can see in the next slide. Okay, here I have listed all the Raspberry Pi stations that are located in New Zealand. In the first picture, you can see there are Raspberry Pi stations all over the world. But in the zoomed in picture, you can see this is a map of New Zealand, and there are the Raspberry Pi sensors that are located here. So to create a list of these stations, I have used some web scraping tools and Python script. After doing that, there was like approximately 70 stations all around New Zealand. So now I have complete information about these stations, like those have the information about the channels, the latitude, longitude of the station, the time of availability. Because when I check that these stations are not always active, sometimes it is active, sometimes inactive. So when these are active, we can get the waveform information from them then. So after listing out the 70 stations, approximate 70 stations from New Zealand, I had to filter out these stations. In the next slide, you can see. Okay, a station have different kind of channels. Among those, the earthquake waveform I have here, I had to collect the data set of earthquake waveform. I needed exactly these 4 types of channel. These are E, N, and Z. So if these channels, exactly these 4 channels are available in one station, like if this 4 channel is available in this one station, then I can include it to my station list. Otherwise, I have not. So there is an analysis that among those 70 stations that is located in New Zealand, I got like 47 stations that have these 4 channels to have the earthquake waveforms. So after filtering out these stations, I have all the information about the station related things. So that is one part of my work. My another part of work is to create the earthquake information. So for this, I have used the GeoNet server. GeoNet server is like that. It basically provides you the earthquake information that occurs in New Zealand. So here you can see the big picture. Here it is a GeoNet query. You can give all the parameters. I inserted like the time range I want to collect the earthquake data. And then after the latitude and longitude of New Zealand, because I have to collect within New Zealand. And after that, I have done the minimum and maximum magnitude. The minimum magnitude was like 2.7 and maximum was like highest recorded. So if I give this parameter as a query, they will provide me with a CSV file. In the CSV file, I have a different type of information about each earthquake event, like the time of the earthquake, the location of the earthquake, and magnitude, latitude, longitude, and other stuff. So from that, I have created next slide. Okay. Okay. From that, I have created like I have information about the earthquake from 2019 to 2024, and the latitude and longitude. You can see this is of the New Zealand map, and the minimum was 2.7 to maximum like highest recorded needed. And after that CSV, I have now 2 tasks. Next slide. Okay, I have now 2 tasks. One task was that all the information about the Raspberry Pi stations that I have told you earlier, and another is the earthquake related information that I have collected from GeoNet. So by collaging these 2, here comes my main work. I had to create for each earthquake ID, I had to check if those earthquake waveforms are available in the Raspberry Pi stations. If those are available in the Raspberry Pi stations, then I have included those in my dataset. And if not, then I have not. So the dataset now have 2019 to 2025 range, and there was like more than 10,000 records of earthquake. Next slide. Okay, here you can see an overview of my dataset. There is, you can see more than 10,000 of earthquake records that covers data from 2019 to 2024. And the magnitude was minimum 2.7 to highest recorded. and each record spans for a 3-minute time window. Like I have taken, let's assume there is X second. At X second, the earthquake has started. So for that, I have taken 1 minute before the earthquake time and 2 minutes after the earthquake time. So total a 3-minute time span window, so that we can collect all the peaks. I mean, what you call in general form like earthquake shaking. We call it in peaks. To collect the earthquake peaks, that is a 3-minute time window. And each file includes those 3 traces, like I told you before, E, N, and Z. And for the station listing, since you can see for if the earthquake magnitude is like lower from 2.7 to 5.5, then I have taken the station that within the radius of 100 kilometers, because when an earthquake happens, the farther station you choose, the more noise you get in your earthquake waveform, which is not good if you work on it, that type data set. So if the magnitude is more than 5.5, then 150 kilometer range is okay. So this is all about in my data set. And currently we're planning to publish an open source database in CRISiSLab that has and there you can see, I mean, the seasons that have many kind of earthquake related database and models. And currently we're working on New Zealand within New Zealand, but we are planning to expand it outside of New Zealand if we can do it successfully. So yeah, that is to sum up all my work.
Thank you, Tasvia. So maybe I will ask Tasvia's mentor, also our PhD student Danuka, to tell if you need to share the slide. And yeah, Danuka, please tell us a little bit about Tasvia's work and how her project contributes to your research project. Thank you. And Tasvia, maybe you can mute yourself.
Okay.
Thank you. The big meeting room needs to be unmuted, please.
Yeah, hope you can hear me. So thanks, Tasya, again for the great presentation. So collecting earthquake data is a pretty straightforward task, and like there are several earthquake databases in the world right now. Probably you have heard some well-known databases like State and Instant and so on. So these databases are used to develop algorithm which will be essential in earthquake monitoring, earthquake detection, earthquake phase seeking, and so on. So currently, New Zealand has a well-structured earthquake repository in GeoNet. More than, I guess, more than 12 years of earthquake data. And what Tasvia does is, okay, so GeoNet has this very high-tech sensors, but when it comes to low-cost sensors like Raspberry Shake, we don't have current database, I guess, all over the world right now. So we are starting to create a database with Raspberry Shake within New Zealand, so that we can adapt whatever the algorithm we are developing using these well-established databases to low-cost devices. So that is major contribution, and of course, like earthquake database will be eventually important in many cases, not only for earthquake tasks, like other tasks as well.
Cool, thank you, Danuka. And Martha actually asked a question in the chat. She said, "Thanks, Tasvia. But what were the 4 components you were getting from Raspberry Pi? Because usually 3 is what they're looking for." Tasvia answered.
Yeah. So Raspberry Shake sensors has Raspberry Shake itself has different sensors. So
mostly TASVIA is working with Raspberry Shape 4D sensors. So they are the most available ones in New Zealand, and most of them are deployed by CRISiSLab itself. So Raspberry Shape 4D sensors has 4 channels. So 3 of them are acceleration data in three directions. That means 2 horizontal directions and 1 vertical direction. And another channel is this Geo4 that is giving the beat motion data. Probably you can say as velocity data, not acceleration data. So that is also very important and with different characteristic than acceleration channels, but it's useful.
Yeah, thanks. And hope that answers your question, Martha. And if not, we still have time later on at the end of all the presentations, and we can continue this discussion. Thanks, Danuka. Thanks, Tasvia. And let's move on to the next presentation. Also, one of Danuka's interns, Vijith, and his presentation will be on adapting PhaseNet architecture for real-life earthquake detection. So, Vijith, over to you.
Yeah, can you see my slides and am I audible? Okay. So good morning, everyone. I'm Vijit Manasiri, currently an undergraduate student at University of Matua, Sri Lanka. Over the past 6 months, I have the incredible opportunity to intern at CRISiSLabs with Mr. Dhanuka on solving real-world challenges in disaster management. A bit more about me beyond the university. I'm very passionate about understanding how the world works. That curiosity is what led me to CRISiSLabs. I attended the disaster management conference back in December, and I realized it's a lab that fosters collaborative research and good place to contribute. Through this internship, I witnessed how research translates to action and how a little contribution like mine can make a world a safer and a better place. During the internship, our main focus was to push the boundaries of real-time earthquake detection using AI. So that's why this presentation is titled as AI at the Edge, where we aim to bring intelligent monitoring to the edge. Moving on. So let's begin by understanding what earthquakes and early warning systems are. An earthquake occurs when sudden energy is released within the Earth's crust, creating seismic waveforms. These waveforms include P waves, which are weaker and the faster ones, and the S waves, which are slower but more destructive ones. The goal of an earthquake early warning system is to detect P waves and alarm when S waves arrive. So these earthquake early warning systems come in 2 types. Centralized systems where all the data comes from all the stations and get processed centrally. Decentralized systems where detection happens directly at the location. However, traditional centralized systems, they face issues like latency, bandwidth, and sometimes it might go down during the disaster. So this is where earthquake detection using AI on edge devices become in handy. Okay, so in the lab, we focus on implementing decentralized earthquake early warning systems. For this task, detection at the edge is very important. So we explored some of the existing models like PhaseNet, equity transformer, GPT, and thread models. And our focus was mainly centered around PhaseNet because it was widely used, well-known, and have a decent accuracy in detection, seismic picking. So if I give a brief introduction on PhaseNet, it is a deep learning model that assigns probabilities to P waves, S waves, and noise. However, it was originally designed to work with long 30 seconds waveforms, which is long for small devices like Raspberry Shakes. So my task was simple. My task was to adapt it for short time windows like 1 or 2 seconds while maintaining accuracy. I simplify the model and reduce the window size and focus on the question, is this an earthquake or not? This made the model much faster and lighter. ideal to use it on edge devices. So if we talk about the results, despite the simplification, the performance of the model is comparable to the original PhaseNet with the key evaluation metrics like precision, recall, and F1 score. So as you can see on the left-hand side, you can see the performance of 1 second windows, and the right-hand side, you can see the performance of 2 seconds windows. And next. My next task was to explore further possibilities that could make earthquake detection at the edge better. So while I was investigating, I saw even though the optimized PhaseNet works, it still needs large label data sets. To overcome this, I developed a semi-supervised anomaly detection framework called QuakeGen. So it's like ChatGPT, but this focuses on detecting earthquakes. The basic principle of this is it learns the patterns of seismic noise, looks like, and flags anything unusual, like an earthquake. Okay. So the QuakeGen has three main components. First one is the encoder, the second one is decoder, and the discriminator. First, what the encoder does is it takes seismic waveform and turn that into a compact version, like a summary. Then decoder, what the decoder tries to do is, then it tries to rebuild the original waveform from the summary. So together, the encoder and the decoder together, they make the generator. At the same time, the discriminator is trying to tell whether a waveform is real or regenerated from the generator. So those two parts, they play the generator and the discriminator, they are playing like a game to regenerate the best waveform. Unlike these traditional GAN models that just measures how close the output is to the input, I used three losses. These three losses: adversary loss to tell how realistic the reconstruction looks, contextual loss to say how similar the waveforms are, and the encoder loss to say how these summaries match. And so after training, the model becomes very good at reconstructing normal signals. So when an earthquake occurs, there will be high reconstruction errors. So if we talk about the results, so these are reconstructed results. So as you can see on the right hand side, both the contextual loss and the encoder loss, they steadily decrease, indicating that the reconstruction learning happening well. However, the adversary loss remains relatively unstable, and to be honest, it was a bit of a headache during training. Later, I figured out that is typical for GANs. Despite this, the overall loss, the weighted sum of all components continue decrease. That is what it all mattered. As a result, QuakeGen produces high quality reconstruction for normal noise, that means non-earthquake signals, and high reconstruction losses for earthquake events, enabling detection without label data. So moving forward, we have planned to test the PhaseNet architecture on real-time data using edge devices. Because we couldn't do that, I was testing and cross-validating, and continue further refining of QuakeGen to improve its performance. And these steps, I believe these steps will help us to build a decentralized earthquake early warning systems with smaller time windows and minimal label data. That brings me to the end of my presentation. Thank you all for your time and attention. Now I'm happy to take any questions. Thank you.
Thank you, Vijith. Pradeep has a question for you. What is resource requirements for training these algorithms?
Resource requirement in the sense of company power?
Yeah, he said yes.
Okay, computer for the computing power, the model size should be minimal. That amount around. So we are talking about Raspberry Shakes. So Raspberry Shake. So Raspberry Pi. So we had to minimize the model size. So normally, FaceNet is around, I guess, 32 MB if I'm right. So I have reduced that to 2 kilobytes. So that is kind of yeah. So if I did I answer your question?
Yeah, feel free to unmute yourself, Pradeep, if you have further following up.
Thank you. So that's great. Reduce into 32 MB to 2K. Thank you very much.
Yeah.
Any other questions? And if not, Danica, feel free to, if you have anything to add for Vijay's presentation, feel free to give us more context.
Okay, thanks Vijit for the amazing presentation and amazing work. So basically what if I explain what he does was like for earthquake monitoring, we have very saturated models, namely called PhaseNet, EQ transformer, GPD, and so on. So, but the problem for real-time earthquake detection is there is no such kind of state-of-the-art models that can consume short input window and detect the earthquake in real time. So that is essentially real-time earthquake detection and earthquake early warning. So that's Vijit's projects came into play. How can we adapt these existing models to detect earthquake in real time and whether check whether they are successful or not? So there is kind of an overview. So to give so that and again so he has adapted this PhaseNet architecture, so we can make this as a reference to our work while we are training our own models. So we are deploying our models more or optimized for Raspberry Shake, so that we know, okay, for 2 seconds of window, we can go for this type of accuracy likewise.
Cool. Thank you, Danuka. Yeah, thanks Taspia and Vijay for your presentations. And for people who are going to the QuakeCore annual meeting in September in Dunedin, and so Danuka is actually going to, he's one of the lightning talk participants. So yeah, feel free to show up for more content. Cool. So the next two presentations are about LoRa sensor, long range sensor. And are you going to do this presentation together? Yeah, Megada and Toby. So their titles are Deployment of an Alternative Low Power Emergency Communication Network using Meshtastic LoRa devices and the Development of a Network Management System, and Meshtastic LoRa Network, Backend, and Firmware Development. So over to you both.
Hello, good afternoon. I'm Megada Pereira. I'm a fourth-year software engineering student at Victoria University. I started my internship here in November 2024, and February this year, I started working part-time. So today, Toby and I will be presenting the current state of our research and development into a LoRa network for emergency communications and the management system we're creating around it. The current purpose of this research is to provide a way for people to stay connected to their friends and family during natural disasters, but while also allowing us to manage these devices remotely while they are placed in people's houses. But CRISiSLab's end goal for this project is to make a network to maintain communication with other CRISiSLab projects during disasters as well. Oh, yeah, okay. So, So why are we not using existing communication technologies such as broadband or the mobile network? So the reason we're not using them is because they use a lot of infrastructure that's very power hungry. For example, broadband, you must have a router at home, ONT boxes, and other stuff like that. And the mobile network has a lot of very powerful antennas dotted around the city. And when a natural disaster shuts down the national grid completely or partially, the infrastructure of these networks will not really last long on their backup power sources. So instead of those networks, we've decided to create a network out of LoRa devices, more specifically the LilyGo TV, which I have one of here in the room. It's able to send messages over many kilometers without relying on public infrastructure like mobile stations. It can also run for extended periods of time on battery backups, which is very useful for emergency situations. So what is LoRa? So if you don't know what LoRa is, it's another way of sending data over the radio waves, similar to FM, which is used in radio stations for getting music to your car. However, instead of FM sends data encoded as the change in frequency, LoRa sends these increasing and decreasing frequency patterns, as shown in this picture. Each different pattern is a different symbol, which is a bit more complex, and so it limits how fast we can send data. However, the unique shape of the signal means that receivers can understand it even when there's a lot of interference involved. So since the signal is much more resistant to interference, the devices using it are able to transmit with lower power and still get heard, which is one of the reasons that their batteries last much longer. So before we started deploying the devices and developing a management system, we did some testing to figure out its limitations. So we tested in 3 locations initially. So the middle one is Macro Beach, the one on the left is Island Bay, and the one on the right is Cuba Street, which is in the middle of the city. So for each of the tests, we would go to the start point. Usually in these pictures, it's the bottom. And for each test, we would increase the distance between each node until it would fail, and then come back and start testing how long it would take messages to do a round trip between one node to the other and then back. And then we'd test it for each different radio setting. And then once we'd done that, we'd make that middle one a node and keep going and do the same tests. So from the results, we found that all the devices could send up to 2 to 3 kilometers with direct connections. However, in places with a lot of buildings, like Cuba Street, for example, the range would decrease to just below 1 kilometer. But we found that if you increase the height of the node a bit to the point where it's above all the surrounding buildings, or the range issues are largely mitigated. And from the speed tests, we found that the average speed was approximately 3 seconds for round trip, so 1.5 seconds each way when connected directly, and approximately 6 seconds when there's one hop between them. And so with this information, we decided to continue with our deployment. So the initial deployment started after the main internship. So this is after February. And most of the devices were hosted by volunteers at CRISiSLab, and some people from outside CRISiSLab, like GNS. And we also chucked some sensors up in Victoria University and Massey to improve their coverage of the Wellington area, since they were high up. And once the deployment was finished, we did a test where everyone that was available would send a message on the group chat. And from the screenshots that I got back, I was able to deduce that Aotearoa in the top of the picture and Kilburnie in the right were not connected to the central network due to physical obstructions, which is the high-rise area and the mountains between Kilburnie and the central Wellington. But after switching to the public network, most of the holes in the network were filled except for the high-rise areas themselves, you can't get any reception in there. Now on to the management system. So from around January 2025, Toby and I, we have been working on a system to remotely monitor and manage the network. I had experience creating web apps, so I decided to handle the front end and authentication server. It's written in Rust using the Rocket framework, and the web app itself was written in React. Each pin on the map is a device in the network. Currently, they're all over the place in the world because I used randomized data during development. So in the future, this will all be within New Zealand. When you click on a pin, it'll show a pop-up with some information about the device, with a link to a page where you can get more in-depth information. And each blue line is a route between nodes. Currently, when you click on it, you will only get which nodes are connected. But in the future, you'll get more information, such as the signal strength between them. This is the node search page. So when you go here, you can search for a node based on all of its identifying tags, such as the ID number or username. And it also has a link to the in-depth information page, which we'll show next. So this is the node information page. So when you're logged in as a normal user, you'll get only the section on the left, which is the node information page, which displays every single piece of information each node will broadcast to us. And then if you're logged in as admin, you'll see the right pane. Currently, it's in development, but in the future, you'll be able to send commands directly to a device in the network, and thus it'll let us change the configuration of each device in the future. And it's the final page, the accounts management page. This is like for admins and users to just reset passwords and stuff. So as a normal user, you'll be able to reset your own password and that's it. And as an admin, you'll be able to add and remove users and change people's passwords for them. And so that's all the functionality of the web app. I'll pass it on to Toby to explain the design and functionality of the servers and firmware.
So everyone fix this, pause and let them change. Kia ora, I'm Toby. I'm from here in Wellington and I'm in my final year at high school at Wellington High. I joined CRISiSLab through a competition last year, which Raj mentioned before, which they run annually, and that led to a small internship at the beginning of this year, which led to my current internship working as a research assistant on this project.
Yeah.
This
talk, it's working.
Okay. So in this high-level diagram, the client on the left is Migada's job. That's basically everything that the user would see in the system. And then my role is the bit in the circle, so the software on the radios themselves, and then server, which is an intermediary between the two. Writing software for a LoRa radio from scratch would obviously be a huge job. So luckily, there's a project that already exists called Meshtastic. It's an open source project, including software for the radios themselves and apps which you can use on a phone or computer if you're connected to a node by Bluetooth, Wi-Fi, or cable. Meshtastic is also a decentralized system, which is great because in the case of a natural disaster, you don't have any single point of failure. On Meshtastic's apps, you can display other radios on a map. You can see some key information like names and battery levels. You can send messages either directly to another node or on a shared channel. You can collect telemetry, so basically live metrics from your node, or you can request it from others. You can configure your node, so changing settings and things like that, or you can remotely configure others which have been configured to allow you to do that, or you can trace routes between your node and another. So it's a good start. If we expand this very high level diagram, this bit around in the circle is the mesh, so the network of radios, and the orange nodes, they don't have internet, so maybe they're at the top of a hill or wherever, and these red ones, they do have internet, so perhaps they'd be at someone's house. And And those gateways, which have internet, are how we can connect our mesh to the server via an MPT broker. I won't go over that if you've never heard of it. You can basically pretend it's not there. Basically, it's just improving the reliability of the connection between gateways and the server, which can get permission to the client. So if we imagine we're this node at the bottom, we could potentially talk to the client through this route or any other possible combination. And that brings us to the first problem, which is that Meshtastic can't really do that. It uses a method called flooding instead. So what it would do is if we're that blue node at the bottom, it would send a message out to its neighbors, and then those nodes would send a message out to their neighbors until it gets to a gateway, and then it can go from a gateway to the client. This method works great for a decentralized network because you don't have to look at the whole network holistically to work out the best routes. But even though Meshtastic has done this in a much more optimized way than I've explained here, our message still has to be forwarded a lot of times between nodes to other nodes which didn't even need the message. So it's not as good as just doing this if we knew where to go. Our solution to this is when the mesh starts up for the first time, every node sends a message to its neighbors, and from that we can extract signal data. So for example, this node here would send a message to all of those 3 orange nodes, and now those orange ones know the signal strength between the blue one and themselves. And then this node would do the same thing, and if every node does that, and sends the signal data that they've gathered to the server can reconstruct a graph of the network and determine for each radio which other radios they should try to hop to first in order to get to a gateway, and therefore to the client. So example, once we've done that, is if we're this blue node again, we might know the next best hop is to go to that orange node, and then that node knows that the next best hop is to go straight to this gateway. But also we have some redundancy. So if, say, for example, we made it to the orange node, or this green one now, but we didn't make it to the gateway on the right, it knows that the next best option is to go to the orange one on the left, and then the same thing repeats until we get it. Another useful effect of having that data, we can send it to the client and use it to start to visualize network topology. So that's what Megata was talking about earlier. That's how that page works. And you can't see on this image, but it's also possible to color code those lines so we can see which parts of the network are stronger or weaker, or where we could improve it. Live telemetry. So this is really important for monitoring a system. We need to be able to look at the entire mesh and make sure that all nodes are functioning properly. This is something that Meshtastic does have, but we still have to be connected to a node with another device, and that node will need to be able to reach every other node in the mesh, which is obviously not realistic at all for a very large mesh. And even if we could do that, we don't have much control or flexibility of what metrics we get. So part of our modification of Meshtastic's firmware involves sending our own telemetry from every single radio at some interval to be accessed on our own app. Megata mentioned some future plans before, but I'll just remind you in case you have any technical questions about them. Firstly, gaining remote control of any radio in the network for configuration purposes. Requesting telemetry from any single radio on an ad hoc basis. This is really useful if we're concerned about a particular node and we need to see what's happening with it right now. Using the system in a decentralized manner if required. Obviously, it's great if we can make this new system with all these extra tools, but if we can't use it when we don't have internet, then that's not very useful. And storing telemetry in a database for long-term statistics. I understand I've glazed over many technical details due to the time that we have, but please ask any questions if you have any.
Thank you both, Megata and Toby. Yeah, so Raj, this is your project, long-range research. So maybe you can give us something to add on if you want to.
Yeah. I mean, that's awesome work. And so just to give you context, I mean, in a couple of minutes, so we have been looking into LoRa as a technology when internet is not available. So there have been a lot of work going on behind the scenes in addition to what Migada and Toby has been doing. And at the moment, there are two honors projects working on some complex AI methods to completely revamp some of the protocols we are using in the LoRa. But what Migada and Toby is doing quite essential, where we are setting up a backbone of LoRa-based sensors, where we are using current platform called Meshtastic to do that. So without having a platform, we can't do those complex tasks. So it is essential what they are doing. So what they haven't mentioned is that the number of units we are deploying, we have 100 sensors to deploy in Wellington area. So probably towards the end of this year, we'll have CRISiSLab will have 100 sensors, LoRa sensors, but after we have started doing this, we found out that there are nearly 300 other public sensors, and they are quite keen to engage with us and working with us in collaboration to expand the network. So hopefully sometime next year, with all what we are doing, we can kind of probably adapt these Wellington-based network to issue earthquake early warning, where we have our locus earthquake early warning network. We can piggyback this with our Raspberry Shake network, and without internet, whether we can actually send warnings or get building instrumentation data out without internet, and these kind of other use cases apart from in between end users to send messages. So there are bigger research coming up or building up on this platform, but essential to build this platform. And Migada and Toby, they are doing a great job. And hopefully some of you may be engaging in the future as well, as we are deploying these sensors in the Wellington region in the near future or next few months. Yeah, I hope that's enough for now.
Yeah, thank you, Raj. Any questions from the crowd? Yeah, I know that a few of us have had this LoRa sensor at home already, and Migada has been engaging with us in terms of what can be continued. So it's quite fun to just kind of be part of the network and see other networking dots, and you can even send messages to each other. So yeah, as a kind of like an outsider, I found it pretty fun. So other people can get involved, get in touch with them after this webinar if you are in Wellington and want to be part of this communication network. Because potentially it will be, it's kind of towards what if the internet is down, and how can we still keep in touch with each other when the disaster happens, stuff like that. Derek is asking, what is the battery life?
So the battery life of these devices running full tilt continuously with these batteries, 18650s, is about 1 day at the most currently. But with bigger battery packs, they'll last much longer. There's other devices that last many days on a single charge. So it really depends on what's on the device. Like this has GPS, which drains the battery a bit faster. So you can turn stuff off, optimize it for the situation, and get the kind of battery life you need.
Yeah, I like to add a little bit. I mean, we are not considering about the power consumption yet, but that's another big part of research we are doing at the moment somewhere else, how we can optimize the use of the existing battery. And there are many other ways we can extend the usage from the software side as well as the actual battery side.
One more thing is that they only use a little power at once, and so these things can also be one-off solar panels. A lot of nodes outside that people have deployed are solar panel based, and they have a small battery for backup, so they can keep running at night. And so when the sun comes back up, it recharges, and so they really never have to go out and recharge the batteries at all.
Yeah, thank you. And then another question from Steve. So can the management tools work through the mesh only, or is it relying on the MQTT server gateway?
So currently it is reliant on the internet. So yes, the gateways and the MQTT broker and the server. But the end goal is to be able to take the system and also be out in the field using it in a decentralized way as well.
Yeah, I mean, it's mainly to monitor the network performance, but it is not going to impact the actual communication if internet is not down. But this is useful for us to monitor what's going on. But as Toby mentioned, we try to completely work independently from MQTT in the future. So that's the plan.
And kind of a follow-up question. Yeah. So I believe now we are currently pulling the data from the servers, so like the sensors, LoRa devices. If an earthquake or disaster happens, when the internet is down, how would you like collect the stored data from the servers, the sensors, the devices? I mean, like when the internet is down, you can't send the data to the
when the internet's down, the server becomes completely out of the question. And eventually we want the system to be able to work when you're connected to a single node like Meshtastic.
How would you get the data that is recorded? I mean, like pass between the sensors.
Well, it can just go through the mesh.
You can.
So the server's completely out of the equation.
And then like if you want telemetry data that happened during the disaster to get the data that is happened that communicated between the sensors. After the disaster, the network is established after the disaster. How we can do that? Do you have a storage capacity inside the sensor?
Inside the device, I think we haven't set anything up to store it, but yes, that's possible. But I think I don't remember how much space there is, but it's very small.
Yeah, I mean,
I have to check how big it is. But
so just to add to the context, I mean, at this stage, the priority is we haven't really thought of like as Toby mentioned, there'll be a method. I mean, hopefully we'll develop a method to use infrastructure-less way to monitor it. It's just to monitor it. But I mean, they haven't gone into that stage yet. So at the moment, we'll have to go through the MQTT server. But most important thing, at least by the time when disaster hits, if we know at least there's good enough nodes, so they can be independently talking to each other. So they themselves can have some sort of idea what's going on in the network, hopefully. But it's an important question.
As we can feel that I think it's an important start to think about how communication can be without internet. And all those questions just make us realize how tricky it is since we're so used to internet and we sort of take it for granted that we have internet. So I guess it takes time, but it's a start. And if anyone else have more thoughts into it, and please get in touch afterwards, get in touch with Raj. And it's only a start, but it's an important one. So thank you very much. So that were two presentations on long range sensor. And now let's move on to the next one, Robin. He will be, so the next two presentations, Robin and Delani, they are interns from our PhD student, Alfredo. So maybe I try to change that a little bit. Before their presentations, Alfredo, do you want to tell us a little bit about your research and the context of their contributions?
Sure, Adesia. Thank you for introducing. Yes, we have two very good interns, Dilhani, that sadly is not connected, but she sent the video, and we will see in the couple of minutes. And Robin, that is helping in the project with the geometric rectification of the image. So I will explain a little bit, because we are changing of natural hazard now, and we are changing about the main topic. This project is about CTC signs to monitor how we can use CTC signs initiatives to improve the monitoring of coastal cliff landslides. in New Zealand, and maybe in the future we can extend to the world. For this, we are using or we are testing 3 different CTC science initiatives. One of that, Robin will talk about that is CRISiSLab. That is an initiative to monitor shorelines, and he was trying to adjust that methodology to focus in the coastal cliff. And with Ilhani, we was trying to use that kind of photographies or image that the people is capturing for us in 3 different study sites, in this moment in Taranaki, in Auckland, and in Hawke's Bay, specifically in Cape Kidnappers, in Hastings. The people is capturing some photos and submit to us, and we are using that kind of photos to understand and to identify some features or some signs to trying to monitor and understand the coastal cliff behavior. So yes, that is in small words, in short words, the project. So yes,
thank you.
We can continue with Robin.
Yeah, thank you, Alfredo. Yeah, Robin, the floor is yours, and please share your slides.
Sorry, give me a second.
Yeah.
Sweet. Can everyone hear me?
Yeah.
Sweet. So I'm Robin, and I was an intern under Alfredo, and my focus, as he was saying, was the geometric correction of the citizen-based coastal monitoring. I'll just quickly do a brief introduction about me. I'm a data science student, so my focus is mainly with machine learning and AI. I've never worked with visual data to do with image processing or anything like that, so this opportunity was quite interesting for me. But a lot of the techniques and things that I picked up along the way as a data science student helped me understand how we can use image processing techniques to help monitor coastal cliff and the landslides associated with them. So just quickly, I'll build on some of the things that Alfredo was saying. Monitoring coastal cliffs and the landslides and the hazards that they sort of produce is quite difficult. Unlike floods or earthquakes, there's not a lot of like readily available data for us to, or means for us to monitor the sites where these disasters can occur. Currently, there's a lot of drone mapping and also surveying to try and map or track changes within the sites to see if these landslides are becoming to see if landslides could become a problem later on, or yeah, so it's quite hard for us to determine whether the state of the coastal cliffs is dangerous for people to be around. So as Alfredo was alluding to, we wanted to produce a sort of means to get images from publicly available images and see if we could track features from them to sort of get a better understanding and a more readily available understanding of how these coastal cliffs are sort of doing over time. Yeah, as I say in this last bullet point, it makes disaster management for locations like this a lot harder when we don't have sort of readily available data on the state of the cliffs. So my focus at CRISiSLab was the geometric mapping of images using a technique called photogrammetry. So the CoSnap process was an initiative that started in Australia. They used lots of pictures that they took, or that the public took, of lots of pretty beaches around the coasts or the east coast of Australia. And they took these images and they took these images and were able to geo-rectify the images to show where exactly the coastline or how the coastline is changing over a long period of time. So the importance of mapping the coastline geometrically is that they are able to track the coastline in real world space with geographic coordinates. They can anchor the shoreline in geometric space instead of comparing pixel by pixel. When you're comparing two images, it's difficult to know how far exactly the coastline is pushing back, or if it's moving forward, or whether anything is actually changing at all. So by geo-rectifying the process or geo-rectifying the image, you can see in this second image, there's an actual, there's an actual representation of that image in a geographic space that can be compared image by image. So the process of this was quite complicated. They estimated the, sorry, I'm just getting a little lost. Give me 2 seconds. Right, so instead of measuring changes in vague pixel distances, we can compare models with different time periods with high precision. So they can, sorry. Oh, sorry, here we go. The process involves calculating a transformation based on known camera parameters, pre-existing ground control points, to provide an estimate of the images that can be compared in real-world space. The COSNET methodology had anchored the coordinates of the images to geographical coordinates and could do this to view the shoreline from a top-down view. The problem that we faced was that a top-down view for the coastal cliffs was neither possible nor useful for our purposes. We wanted to track how the cliff face was changing from a side-on view, as you can see from this very hastily drawn rectangle. If we can view a side-on view and map this and create a geographical representation of how this is changing over time, this would prove a lot more useful in monitoring the coastal cliff faces. Trying to figure out how to do this and augment their already complicated transformation process proved a little bit more difficult than we initially anticipated. Lots of their parameters that they had estimated for were already unknown, and it was a lot more difficult to find a way to map or estimate with ground control point with the little ground control points that we had. If we are able to do something like this, we can get a much clearer picture of how the cliff is behaving over time and track the features in these images to see how the state of the cliff is changing. Other solutions that we sort of looked into, there's a technique called structure from motion, where we can use overlapping photos of different images, usually from a drone or a handheld camera. We can estimate depths and shapes of different features of the cliffs to see how the cliff faces. You can see in this picture, it creates a better depth understanding of the cliff face itself. So if we were able to create some sort of visualization of the cliff face in this manner, we might be able to get some more accurate and valuable insights about the state of the cliff face. This really works a lot better than, this would work a lot better than the photogrammetry techniques that we were using before, but it's a lot harder to, we don't have the data and lots of images from different angles of the same cliffs. That's another problem that we kind of ran into, that data scarcity of cliff images. And Yeah. Yeah, sorry. Thank you for listening. I hope this was.
Yeah, thank you, Ravin.
Thank you.
Yeah, thank you. Okay. Any questions? So because I know about the citizen science project, and it's actually if you end up in, is this in Gisborne, like Napier area? Alfredo?
What's the location? The location area, Alicia.
Yeah.
We have at this moment 7 stations in Taranaki, in Aotearoa Nurunui. That is 2 small communities in north of Taranaki, north of New Plymouth. 1 station in Cape Kidnappers in Hastings, and recently we installed last month 1 CRISiSLab station, and we improve or we apply another technique based in CRISiSLab, but is just a stainless steel plate embedded in a pathway in Mairangi Bay in Auckland. That is more a residential place in Auckland City with 5 different points.
Yeah, cool. So if anyone happened to be there and participate in the citizen science project by taking photos and upload to the portal. Ravin, perhaps you could unshare your slides first.
Oh, sorry.
Yeah, no, that's all right. And yeah, it's great that you share with us that you're excited to be on this project, even though it's your first time to do this kind of image processing. So all good, good luck with that. And thank you for the presentation. And if there are no questions at the moment, let's move on to the next one from Delani. And I will be sharing the recording.
Sorry, Alicia, let me add something about
yeah, sure.
We're still working in this challenge, the challenge that he was facing about how change or how adjust this CRISiSLab methodology to the coastal cliff is very hard. It's very innovative technique that we are trying, and we are exploring more techniques or more methodologies to use to rectify this kind of images. At this moment, we was performing some TLS surveys in that sites. TLS is a terrestrial laser scanner with help of the GNS people, the engineering geology people in GNS, now Earth Science Institute. So hopefully in a couple of months, we will have more advanced in this topic. So maybe next year in the next workshop, in the next webinar, we can show more interesting results about this. But thank you to Robin to start with this initiative and to face this complex challenge.
Yeah, cool. Yeah, thanks for sharing that, Alfredo. Now let me share Delani's presentation, which is recorded.
Welcome to the presentation. I am going to present the task of image processing in this. Hello everyone, my name is Dilhani Dorangoda. I recently completed my Master of Philosophy Engineering at Auckland University of Technology. Unfortunately, I am unable to attend this session live. I am prepared this presentation with the voice-over to walk you through my project on causal landslide detecting using image processing. I hope this will be helpful for today's session. If I described about the project background, coastal cliffs are prone to landslides due to natural processes like erosion and heavy rainfall. Monitoring these changes is vital for public safety, infrastructure protection, and environmental management. Traditional methods like field inspections and manual mapping are resource incentive. This project explores how image processing can offer a fast, efficient, and automated way to detect coastal landslides using before and after the images. The aim of this project is to detect landslide affected areas on a coastal cliff by comparing before and after images using image processing techniques. To achieve this, I standardized the image sizes, aligned them for accurate overlay, reduced noise using filters, isolated cliff area using a region of interest, and highlighted significant differences caused by the landslide. I began by loading the two images captured before and after the landslide. To ensure consistency, both were resized to 1000 by 1000 pixels using downsampling. The preserves detail while reducing file size. Then I converted both images to grayscale, which simplifies processing by reducing the data to one channel intensity only, while still capturing key features. Next, I aligned the two grayscale images to ensure corresponding features overlap. This was done using feature detection and transformation techniques. Then I applied a Gaussian filter to both images to smooth out minor noise, lighting variation or texture changes that could cause fail detections. In this step, I focused to analyze only the cliff area. I defined a region of interest or ROI. This was done manually by drawing a polygon and also automatically by specifying pixel coordinates. The goal was to isolate the cliff and ignore unrelated areas like sky, ocean, or vegetation, ensure accurate and meaningful detection. After processing, I calculated the absolute difference between the aligned images within the selected ROI. A threshold was applied to remove small, significant variations. The final output clearly shows the affected areas using boundary outlines, effectively highlighting where the landslide occurred. This approach was effective but had some limitations. Manual ROI selection can be slow, and lighting changes between images may affect accuracy. In the future, the method could be improved by automating ROI selection using machine learning, integrating multispectral or 3D data, and scaling it for batch processing to support large-scale environmental monitoring. To conclude, this project successfully used image processing to detect and highlight coastal landslide changes. By carefully pre-processing, aligning, filtering, and isolating the cliff region, I ensured accurate detection of structural changes. Especially, I would like to thanks to Professor Raj Prasanna sir giving me this opportunity to contribute this project. And also, I would like to thanks Mr. Alfredo for providing the project details and images. I appreciate the opportunity to present my work and hope it contributes to future coastal monitoring efforts. Thank you.
Cool. Yeah, that was a recording. Any questions from the floor or from our attendees? Yeah, we can see that a lot of possibilities there from the image processing of coastal snap and something related. Anything there that you want to add, Alfredo?
No, Alicia, not at this moment. If you have or any of the people have any question, I will be attentive to answer at the end of the webinar.
Okay. Then let's move on to our final presentation, and then we perhaps still have some minutes for people to ask questions, some overall questions if they have any. Before Lasantha gives us the final presentation, Raj, do you want to quickly share some of the background or context?
Yeah, thanks, Alicia. So this is kind of a new area we want to expand on at CRISiSLab. So we have been doing a lot of work, earthquake early warning, communication, flooding now, we heard from Olympus. So we want to expand on use of AI and new technologies, monitor landslides. So Lasantha is an expert and he has got background with especially looking into landslides, as well as he's working in a monitoring agency in Sri Lanka. So he has really good professional experience and already published some good articles in top journals. So this is kind of a pet project for both of us to start with the possible opportunities, and hopefully Lasantha will be coming to New Zealand to do his PhD. So that's the long-term goal, to expand on this work. Yeah, and hopefully we are also planning to build low-cost landslide monitoring network in the future using some of the work we have been already doing. So that's a long-term goal.
Yeah, thanks, Raj. So Lasantha will present on automated landslide mapping with free satellite data in Google Earth Engine. And please share your slides.
So can you hear me? And slides. So good evening, everyone. I'm Anta, a geologist from Sri Lanka. Today, I'm currently working at Geological Survey and Mines Bureau as a geologist. So today I'm going to share with you the findings of our recent research on landslides with free satellite data in Google Earth Engine. So first of all, what is a landslide? So landslide is a sudden movement of earth materials down along a slope under the gravity. So it is often triggered by heavy rainfalls or seismic activities. It can cause damage to humans and infrastructure. So landscape mapping is an essential task that because that enforces disaster risk reduction efforts. So what is Google Earth Engine? Earth Engine is a cloud-based geospatial analysis platform that allows users to perform satellite image processing and remote sensing analysis. Google Earth Engine is widely applied on natural disaster analysis such as flood analysis, landslides, and wildfire analysis. Also, it is used in many remote sensing research. So let's focus on Sri Lanka. As we know, Sri Lanka is a tropical country where the rainfall-induced landslides is one of the more major and frequent natural disaster. So, as we can see in this figure, the middle and southwestern parts of the country are the most vulnerable areas for landslides. These are some figures related to the significant events which occurred in Sri Lanka in recently. So, in Sri Lanka, National Building Research Organization is the authorized and responsible organization for the landslide analysis. They conduct landslide mapping, research on landslides, and some mitigation measures. However, they rely on manual mapping. Also, they don't maintain an updated landslide database. And additionally, they often miss the remotely occurred events. So more importantly, in Sri Lanka, there were limited studies on landslide, free satellite images, and machine learning technique. So our aim of this project is to detect landslide in that study area using freely available satellite images on Google Earth Engine, integrating machine learning techniques. The main objective of our research is to detect landslide using Sentinel-1, Sentinel-2 images, integrating machine learning techniques on Google Earth Engine. Additionally, we aim to identify best detection models for the study area, highlighting key challenges. To achieve these objectives, we followed a three-phase methodology. The first one is the data collection and pre-processing. Under that, initially we selected a study area, then we collected and prepared a historical database which is containing the historical event of that area. After that, we prepared satellite images and relevant remote sensing data for the analysis. During the second phase, we have prepared required data for susceptibility modeling, such as spectral indices, topographic data. After that, using training data sets and the data in that database, which we have prepared, we have done image classification. Then those images were validated using and those models were validated using validation data sets and the validation parameters like F1 score, precision, and recall. In final stage, we post-process the susceptible models and further validated using the high-resolution satellite images. To do this analysis, we have look at we already use two approach. The first one is individual grid-based analysis, which means the entire area we have divided into 10 grids, and second one is the whole area analysis, because in this approach we analyze and take the whole area as a single unit. The results reveals that, as shown in these figures, both approaches achieve their maximum detections after adding topographic parameters into the modeling process. We can see it is clearly indicated in red circles in M3 models. All analysis, the M3 models got the highest accuracy and highest detections. Then the further results reveal that while the whole area approach provide an efficient solution, the individual grid models showed a slightly higher accuracy and practical solution. Further, the optimum models are able to detect more than 95 of historical events. In this figure, except red boxes, all the susceptible locations were validated using high-resolution satellite images. Then we have performed an input parameter importance analysis. As shown in this graph, we can clearly see the both approaches show the slope was the significant input parameter, and the differential bare soil index was the second most important parameter for machine learning based image classification. Despite the these good results, we have encountered several challenges on this study. The first one is the cloud contamination on satellite images. It was mitigated up to some extent. A machine learning based slope algorithm, which is called cloud scope, and further it is mitigated using median composite images. The second most challenge was the false detection, which is occurred on agricultural lands. in this figure, all the red boxes are false landslide detections, which are actually agricultural lands. These can be mitigated using integration of land use and land cover maps into our modeling process and using object-based image classification method. However, in current study, we didn't use those advanced methodologies for our research. Based on our study, several key conclusions we can draw. The first one is the landslides in Sri Lanka can be accurately detected using freely available satellite images and machine learning methodologies on Google Earth Engine. Also, this approach not only effective in locally, but also applicable for the other resource limited regions in worldwide. We also found that grid-based models demonstrated slightly high accuracy, while the whole area models were more efficient and scalable. Among these input parameters, the slope and differential bare soil index were the most influential parameters in machine learning based satellite image classifications for landslide detection. However, cloud contamination and false detections in agricultural areas were the key challenges. Finally, we have already submitted a manuscript containing these findings to the Journal of Earth System Science, which is currently under review. Before conclude that, I need to mention Professor Raj and myself going to develop a research project on landslide early warning system in New Zealand. Part of this research will be incorporated on that research. Thank you very much.
Thank you, Lasantha. We already have a question in the chat box from Derek. Was there a minimum landslide size at which the model became ineffective at detecting? So for example, it could not accurately detect landslides below a certain size?
Yeah, it is around 100 square meters because we are using satellite images with resolution 10 meters. So 10 by 10 square meter is the limit.
It's a minimum.
Yeah, that's the minimum one.
Yeah, and yeah, as you can see that this presentation by Lasantha was done in Sri Lanka. So I suppose there are great opportunities here in New Zealand to use a similar G. And
yeah,
are there any questions? Derek had a follow-up question. He said, he asked, so potentially a single cell could be modeled as a landslide.
Yeah, it could be a issue, but while the post-processing, we typically remove the individual pixels.
Yeah, and yeah, we maybe one or two more questions before we wrap up. And yeah, before anyone asked further question, just want to acknowledge all of the interns that, yeah, some of you are still in high school, some of you are uni students, and some of you are master students, but yeah, so all of you did a fantastic job in trying to convey complicated technology terms into this presentation today. So of course, like some of us probably had a hard time trying to follow, but that's just natural. But I'm sure all of us learned some technology some way in another. And yeah, appreciate all your effort and as well as the mentors and CRISiSLab staff. Any other questions from the crowd? And yeah, if you heard something interesting, if you think that probably will be potentially applicable in a New Zealand context, yeah, do get in touch. And we do have a lot of talent here in CRISiSLab to provide you with technological solutions to natural hazards. And if there are no further questions, Raj, do you want to conclude this presentation webinar?
Yeah, thanks, Alicia. And yeah, like to thank all the participants, attendees today, and spending your afternoon 2 hours with us. And so as you have seen the breadth and depth of what these interns can do. So they are coming from so many different profiles from high school. Now, for example, Lasanta is working professional, but still have passion to do technology-related research into natural hazards, which is very important. There's a huge amount of gaps in disaster-related domains where we can bring technologies in a meaningful way to support. So the some of the work highlights that. And the other important thing is that going forward, we are about to advertise our next year from summer internships from CRISiSLab. So we are expecting a lot more interest from potential interns, and that also means that there are a lot of opportunities for researchers as well as practitioners who are grappling with some of the complex challenges where if they don't have time or resources, we are happy to be kind of a interface as CRISiSLab, and we can join. So rather than we decide what are the problems, it is good that problems comes from the actual needs. So we can kind of use these skill sets in a more meaningful manner. So I'm really looking forward to kind of do that kind of interfacing through CRISiSLab, identifying good interns, as well as give them kind of more meaningful or kind of where there's value generating issues in the field, so we can get some meaningful outputs at the end. So that's something I want to communicate. So hopefully we will be able to work closely with the professional community, disaster management sector, and researchers who are conducting disaster management related research. So we can be able to support in a more meaningful manner going forward. Over to you.
Thank you, Raj. Yeah, I think that's it. Thank you very much for participating. And this session has been recorded and will be uploaded onto our CRISiSLab YouTube channel as well as website. So stay in touch. All right. Have a lovely rest of the day. Bye. Thank you all. Bye.